Hello there, Physics 30. We are on to Chapter 16, Lesson 4. What we're going to talk about here is basically nuclear reactions. We're talking about fission and fusion, okay, and how they give us energy. So, one thing they noticed, this is based on Einstein's equation, E equals mc squared, right? And what they noticed is that when the particles are together, they generally weigh less or more than when they are separate. And so there's a difference in mass between particles and a nucleus or separate. And so what Einstein figured out is that this difference in mass is actually how much energy is keeping them together. This is that binding energy, right? Right, and it's very, very small, right? It's a very small difference. Like if I was going to be crazy, I'm just going to give like very simplistic example. If this weighed 1 gram, then separate they might actually weigh 0.99 grams, right? And so, but the difference there in mass is actually how much energy it takes to. Um, sorry, I've got these backwards. Right, this is how much energy it takes to separate something, right? Or how much energy it takes. And so it would, when you are separating something or you're combining something, there's a difference in mass, and that difference in mass is contributed to this what's considered binding energy. All right. So the difference in mass. So things don't weigh exactly the same. Now, the reason that no one had noticed this before is that the differences are smaller, right? And so yeah, I put this is 0.01 grams. Now someone would have noticed this, but in reality, it's more like, it's more like this side weighs like 1.000000001 grams, right? And that's kind of the difference, is that there is more mass, but it's very small. And so Einstein noticed this, and then he noticed, okay, well, how much energy is there, and started talking about splitting atoms or combining atoms or whatever. And he came up with the equation E equals mc squared, right? The most famous physics equation of the 1900s. And what the reason this is famous is because it tells us exactly how a lot of things work. And the big thing is it's the equation of the stars, right? It explains how stars work, right? And explains how we can get massive amounts of energy from very, very little things. And then it leads us to the concept of understanding why things can't go faster than the speed of light, right? Because instead of, if you add more energy to something that's going at the speed of light, you actually just get more mass, you don't get more speed. So that's kind of the idea. So when element decays to its individual particles, mass is gained due to the energy it takes to break apart. When an element undergoes fission or fusion, mass is lost due to the energy. And so this is important, is that when an element undergoes fission/fusion, mass is lost due to the energy that is released as heat. That's important because we are always looking for ways to collect energy, right? And so what we notice is that if fission and fusion happens, right? Fission and fusion happens, we get energy just coming out, just free energy, right? And so we're like, oh, let's release this heat, which makes sense because that's how the sun works. So this equation's right here on your periodic table, or not periodic table, sorry, on your data sheet. Okay. One thing you can notice about a lot of these fusion and fission questions is it's mostly about little details and keeping track of your units. All right. So the first thing we talk about is we're going to talk about the concept of how things can be, how electrons can be measured, their mass can be measured in kilograms, U, or this new mass is mega electron volts per speed of light squared. Okay, and so I converted these. I used the first conversion is just use the atomic mass, right? And I just converted them over, right? We know proton, neutron weigh approximately 1 for atomic mass for U, right? And then if we convert them to mega electron volts, we use E equals mc squared to calculate the energy in joules, and then convert to EV, and then the M, capital M, right, means is times 10 to the 6. These are really times 10 to the 6 here, right? 10 to the 6. But we don't write that, we just keep the M at the front. And so we notice is that these are both approximate. And I've done some rounding here. And so we have this. And so, again, the first step concept is that you guys should be able to convert units in every direction here. You have to keep track of your conversions and how to do it and not miss anything. One thing I would write on your formula sheet is that a proton is equal to 1 U, a neutron also, just round it to 1 U, and they're both equal to approximately 940 mega electron volts. Oh, sorry. Divided by SPL 8 squared. Okay. I want you to take note as well is that the electron and a positron, right, they're equal to 5.11 mega electron volts per C squared. All right, it's approximately that, but electrons and positrons, that matters. Now we've got all these little things, little neutrinos and stuff like that. They're measured a little more accurately on the new formula sheet, which most of you should have, but we're not going to use those for anything too complex here. So again, units are going to matter for these kind of questions. So all right, so this one here, okay. Determine the maximum mass that can be created in units of kilograms from 1.025 mega electron volts of energy. So first thing I did here is I took the 1.025 mega electron volts and I put it into just regular electron volts, right, with times 10 to the 6. Then I converted to joules. Then I'm going to use E equals mc squared, and the joules to convert to kilograms. So 1.64 times 10 to the negative 13 joules is 1.82 times 10 to the negative 30 kilograms. All right. And this is what's called mass equivalency. Okay, mass equivalency. Which means that if I took this energy and I turned it into straight mass, it would be that much mass. Or if I took this much mass and turned it to straight energy, it would be that many joules. All right, and so it's just understanding that mass is energy and energy is mass. We just have them different forms. Mass is energy in a different form. Energy is mass in a different form, right? And so this is kind of we have an idea. So we can use our idea by using our experiment using a mass spectrometer. So usually you're going to be given masses in given the masses, and you have to kind of calculate from there. So the mass of hydrogen 2 has been determined to be this number, and the hydrogen 2 atom, when its mass is together, is that. And so we notice that it has a difference in mass, all right? So we can figure out how to determine the binding energy in EV. So the first thing I did here was I took the E equals mc squared, but I put a delta m there to remind me that's a change in energy. So I took the final energy minus the initial, right? Final mass minus the initial mass, right? It's change in mass, okay? And I noticed they're both measured in U. So I subtracted them. They're both measured in U. They need to be in kilograms. So I use the conversion to turn them into kilograms, right? The 1.66 times 10 to the negative 27 turn to kilograms. Then multiply it. Once I multiply it from U to kilograms, I get in joules. So if you use kilograms, you're going to get in joules. Then I convert the joules to kilograms, and it's going to give me 2.2 mega electron volts, all right, which is 2.2 times 10 to the 6 electron volts, right? So again, it doesn't seem like very much energy, but it's a significant number when we start to consider it. So that's that question there. Okay. So scientists with Einstein doing this, they kind of figured out that there's this periodic table you can kind of play with and fidget with. So in 1919, Rutherford was the first artificially transmute an element. So he bombarded a nitrogen particle with an alpha particle, and he ended up getting oxygen. So he realized that you can actually, this is something they kind of suspected happened in the sun. They weren't sure, but they're pretty sure that's what's happening in the sun. Then they started realizing, well, we can actually turn nitrogen into oxygen here on Earth, right? Nitrogen into oxygen is right here. And so what they started doing is they started bombarding these things with high energy particles. Rutherford used radioactive isotopes, but today we use particle accelerators. And what we do is we shoot things. Oh, sorry, I'm tired this morning. I keep yawning. We shoot things, and so we can go up and down the periodic table by doing this. And so what we notice is that if we get anything past uranium, so uranium is number 92, right? Anything past uranium, anything with a higher number than uranium is actually artificial. So uranium naturally appears on Earth, but any of these elements was us taking uranium and accelerating uranium or accelerating an alpha particle and smashing it into plutonium, then smashing it again into californium, then smashing it again into mendelevium, right, all the way up to lawrencium, right? So that's kind of the idea, is that we can keep smashing. Now, some of these elements have been filled in since this periodic table was produced. Okay, so now we're going to nuclear reactions. There's fission and fusion. So we'll start with fission. Fission was discovered in 1983 by Fermi. Okay, fission occurs where the atomic mass is greater than 120. So anytime the atomic mass is greater than 120, for example, uranium-235 is one that goes into fission. And what it is it's splitting. It's splitting. And what it is that the parent particle or parent element weighs more than the two daughter elements combined. And so we actually get fission. Okay, fission, think of fissure, right? We're breaking apart. Okay, fissure is breaking apart. Fission. All right, so we're breaking these things apart. And so we have more mass here and less mass here, right? Which means we're going to have a released energy. Now, the way they do this is that uranium is already relatively unstable, right? It actually is radioactively decays on its own. But we want to control when and where that process happens. And so we take a neutron and we blast it with a neutron. By hitting with a neutron, it actually causes these things to go through this fission process faster, sooner, more quickly, and a controlled time frame. And we use neutrons because, well, if you used a proton, you'd shoot the proton at it, and then they would repel it, and so you wouldn't be able to get the proton to hit it. So you just have to basically shoot the neutron at it and just go from there. When you're doing these, you're going to be more balancing kind of equations, and when you're doing these, is that you're going to end up getting a parent nuclei and a daughter nuclei, and you just kind of balance using neutrons, right? And so it's kind of interesting how that works. All right. So this one here, right? This following fission reaction, so we had uranium. Uranium, we smashed with a neutron. It broke up into barium and krypton, I want to say, but I might be 100% wrong on that. And when we balance it, we did the 92 minus 56 minus 36, that equals 0. So the charge is balanced, so there should be a 0 here. Then we notice that the 235 plus 1 is 236, and you subtract these, and there's 3 left. So there's actually 3 neutrons, right? Which is good, because what that means is that I shot 1 neutron in, got the fission, which is good because it's going to give me energy, but then I also got 3 more neutrons. These 3 neutrons I can then use to hit 3 more uranium. Right? These 3 neutrons I use to hit 3 more uranium. Those 3 uranium go and they smash. Those 3 uranium go and break and they give off 3 more. So now I've got 9 neutrons that can go and hit the next thing. So it kind of starts 1, then it branches into 3 more. Then each of those 3 branches into 3 more, right? And then each of those 3 branches. And so what you get is you get lots of these. And basically, this reaction starts very small, then it's going to get bigger and bigger and bigger and bigger and bigger until you have all these neutrons just flying around, smashing and breaking and opening up the next reaction. Okay? So why does this all matter? Okay, so why does this all matter? Well, the reason this matters is because of the amount of energy that we get from this is quite abundant compared to kilograms. All right, so a typical family car requires approximately 1,600 megajoules of energy to travel 500 kilometers, and if the chemical energy content of gasoline is this, right? So that's how much energy we get from gasoline and just burning it. And so, of course, we can figure that out. We take the number of joules we need, divide by the joules per kilogram, that gives us kilograms. So for gasoline to go 500k, you need about 36.4 kilograms, right? Which is about 40 liters, give or take. Which that's a pretty fuel efficient vehicle, but yeah, you can think about that, 36.4 kilograms. Now, if one atom of uranium-235 with a weight of this weight, it releases this much energy when it goes through fission. So it releases 173.7 megaelectron volts, which is very little, okay? What mass would you need to provide? So the first thing I had to do here was I had to turn out this 173 into joules. So 2.779 times 10 to the 8. So that's how many joules we have per atom. Okay. I also need to take the U and you turn it into kilograms per U, right? Or into kilograms. So then I get 3.917 times 10 to the 25 kilograms per atom. All right. So this is really important that you sort of keep track of what's going on. So now I can take this 1600, so this is the total energy we need, and divide it by this 2.7792 to 711. That's how many joules per atom. And it gives us this 5.75 times 10 to the 19 atoms. Okay, that seems like a lot of atoms. It's 5.75 times 10 to the 19 atoms. Okay, 10 to the 9 is billion, 10 to the 12 is trillion, so we're well beyond trillion, right? Okay, but it's a lot of atoms. This is the interesting part. So if I have the number of atoms, I times it by how much each atom weighs, right? So this many atoms would give us enough energy to move the car. How much they weigh? I need the total mass of uranium that I need is 2.25 times 10 to the negative 5 kilograms, right? So if you think about it, for the gas, right, I needed 36.4 kilograms. So I need 36.4 kilograms to get the same amount of energy of gas. So the gasoline needs 36.4 kilograms, and the uranium needs 2.25 times 10 to the negative 5 kilograms, right? So that's 0.02 grams, essentially, right? That'd be equivalent of 0.02 grams. So 2% of a gram, right? And so you need to start thinking about how much more energy these fusion and fission reactions create than gasoline or coal or burning any kind of fossil fuel. Okay, and so it's kind of this concept of, well, I need a very small amount, right? What else if I had a whole kilogram, right? A whole kilogram of uranium. A whole kilogram of uranium is smaller than your water bottle, right, that you have, and it can give you, enough, let's say, it can give you enough basically energy to move these cars. It can move, 45,000 cars 500 kilometers, right? 1 kilogram of uranium, if it goes through fission and you harness all that energy, right, would be enough to move approximately 45,000 cars 500 kilometers, right? So just kind of an idea on what that kind of looks like and how different it is. So this is a very efficient process. A lot of energy comes from it. All right. So this is the process I was talking about here, where we have one neutron, then we get some extra neutrons, then we get some more extra neutrons, and it kind of goes to that. All right. So that's kind of the interesting product. Is 3 free neutrons. It's possible each of these 3 can induce fission in another, and so we create a chain reaction. So you don't actually need to bombard the whole bar of uranium with neutrons. Just need to get the reaction going. Okay. The one major disadvantage of fission, other than the Chernobyl incident, is that the daughter products tend to also be radioactive. So the products that we get are not products that we want to just throw in the trash can, because they will give off radioactivity and can be harmful to humans. And so you actually just store them. You store them, generally how they're stored is they're stored in steel barrels deep underground. Right, they're stored in steel barrels deep underground, and they're stored there, and they have to be stored, like, some have to be stored for like 100,000 years, stuff like that. And you have to be careful they don't start to leak and get into the water table. You have to make sure no one goes near them. That part, that nuclear waste storage, that is a big deal, and that's something that they're trying to work on, and how to most efficiently store these things, because you just don't want a byproduct hurting people. Right, so you're just kind of weighing the pros and cons. The pros is you don't really need much for raw product. This creates a large amount of energy for a very small amount of raw product. Right, small amount of uranium creates lots of energy. That's kind of the pro. The con side is twofold. Right, there's the fact that we have to store these daughter products, these waste elements. We have to store them for very long periods of time, and we have to pay for the storing them for very long periods of time. We have to make sure no one gets hurt, because that's a big deal. Another one is that when you have a ton of energy being released from a small area very quickly, it's hard to contain, right? And so we are containing this reaction as best we can and trying to slow it down and all this stuff. And so we get things like Chernobyl, or nuclear meltdowns, or if you're like, I think it was Japan built their nuclear power plant on the side of the ocean, and then of course they had a tsunami, and all of the radioactivity that got released during that tsunami was pretty bad. So there's this concept that we have to that nuclear energy is the most efficient, and it's relatively safe. But when things go bad, they go really bad. And so, is it worth it? And that's kind of, your guys' jobs is you go into the rest of the world and you become voting people, and people start talking about nuclear energy, or you become a scientist or anything like that, then you should be informed. You should have an idea. Well, why aren't we using this? Why does everyone hate fossil fuels? Right? Do fossil fuels have more negative than nuclear energy? Why does everyone like solar power and wind? Right? Well, there's a difference there. Solar and wind don't create nearly amounts of energy that gasoline does. Right? So you kind of have to kind of balance that and have a good understanding. All right, moving on. Okay. So when you have the chain reaction being controlled, so you have a neutron gun here, and you have a small amount. Oh, you have a small amount of uranium in here and stuff like that, right? Small amount of uranium, and there you actually break the uranium up and you kind of dissolve it in water, well, a version of water, and you hit this button here, and you fire one neutron. So that neutron gets fired, and it hits this one, right, which splits, and then it sends out three new neutrons, and it hits another three. But it's one of the, and then this one shoots out three, right? One, but these three might not even go in the direction, they just end up going off on their own, right? And so you get a little bit of energy from this, right? You get a little bit of energy from this one, then a little bit of energy from this one, then they kind of shoot off more, and then a little bit of energy this one, then a little bit of energy this one, and this one, and a little bit more, and so you kind of get this energy is sort of building up, or you get energy kind of building up over time, and you're kind of controlling how fast the reaction happens. Okay, if you don't control it, right? If you just take a bar of uranium or something, some other radioactive element, and you fire a neutron in there, and you just let it happen willy-nilly. They're not separated. You're not controlling. You're just letting the neutrons just do their thing. And this is reaction. This much energy, instead of being released over 5-6 minutes, is released in milliseconds, right? Well, that is explosive. That's very explosive, and that's where you get your atomic bomb, right? Bang, bang, bad. Okay, that's where you get a nuclear bomb, right? And this is what was used in Hiroshima, right? So if you go on Google Earth, you can actually like just type in like nuclear bomb craters, or you can just Google and type it in, or click this little link here, and what you'll see is there's all sorts of craters all over the world that were created by nuclear bombs. I can't remember what country it was, but one country wanted to create a man-made lake, and so they actually used nuclear bombs in order to create a giant hole that filled with water. And then they realized that the fish were not so good, and there was bad things happening because there's nuclear activity and all that kind of stuff. So yeah, there's kind of that concept of the difference between nuclear bomb and nuclear power plant is just control. Okay, so how a nuclear power plant works, you can read. I would suggest reading through this. Okay, it makes sense. They work just like any other turbine or steam system, where you really just have to create energy, and the energy creates steam, and the steam turns turbine. That's the main gig. But what happens in nuclear reaction is you have a very small amount of reaction core, okay, and that's going to heat the water as this goes around. That's going to heat this water into steam, and this is 580 degrees Celsius approximately. Since it's 580 degrees Celsius, it creates steam at a very efficient rate, okay, and everything kind of cycles. So these are all pressurized. And pressurized, so the steam can't escape, and then we have a cooling pipe that comes in and actually cools it with water, usually from a lake or something, right? And that kind of creates the steam. There's a little video from The Simpsons. This is kind of funny. You can watch it if you want. All right. This is the same idea, right? We're actually containing the idea, right? And so this is what a reactor would look like. So we're going to fire some neutrons. We're going to fire some into here, some into here, some into here. And what these bars do is they actually stop neutrons from passing through it, um, and then kind of can help control the temperature of the water. And so if you fire one here, this might all react really quickly. Then you don't want anything passing through here. So then you're not going to fire any neutrons here, right? And so when you fire these neutrons, all these extra neutrinos, this is how much energy you can get from this packet. You can't get any more. If you don't have these bars here, all of these particles can react very quickly and very, very rapidly, and that's going to give us a temperature change way too fast. We're going to have an explosion. So we have these adjusters that allow us to control the rate in which all of these reactions happen. Okay, so that's fission. Fission is what we do nuclear power plants with. Fission is nuclear power plants. It's breaking large elements into smaller ones. So now we have the nuclear fusion. This is how the sun works. Through lots of energy and heat, what we do is we take two hydrogen particles and we hammer them together, right? Just by heat by heat and gravity. Let's push them together and they eventually become a helium, right? Keep in mind that hydrogen particles don't want to go together because they're both positive, and so you have to use lots of heat, lots of pressure, and it gets this, right? Then we get an extra neutron, okay, plus energy. And so fusion also creates energy. Okay, and these are low mass, and so this is kind of the idea that you have hydrogen to form helium, then you have helium could eventually form 4,2 helium. Then if you really want to, you could push two heliums together and form a carbon or an oxygen, right? And that's how you get this idea. And you notice what's happening is every time one of these fuses, every time some of these particles fuse, you're going to get neutrino, positron, gamma ray, and each of these little explosions is energy. Okay, this doesn't happen on Earth very much. Right, so that's how the sun works, right? This is the reaction. Fusion creates sun. It happens in the sun. We get neutrons and energy coming from the sun to us. Okay, it's really high temperatures and gravity. Okay, controlling a fusion reaction is extremely difficult. Hydrogen must be heated between 45 to 400 million kelvins, 45 to 400 million degrees. Then you have to have lasers and magnetic fields that are used to treat these high temperatures, but they can only be sustained for a few seconds. They don't generate much more energy than they had put in. And so what you have to do is you actually have to put a lot of energy into these things, okay? And you get very little out. Whereas a nuclear fission reactor, you just shoot a neutron in and it starts giving you energy rapidly, right? And so there's kind of a difference here, okay? Deuterium and tritium are basically the reaction of two heavy isotopes of hydrogen. As shown, the product is helium and a lot of energy. So this is the only one we do on Earth, is we take deuterium and tritium, we add a bunch of fuel, heat, all this stuff, and we can get helium coming out and neutron, and that kind of gives us a little bit excess energy, okay? So it gives us some plus energy, but it takes a lot to get it going, and it doesn't last very long because it uses up these raw materials very quickly. Sorry, I know this video is getting pretty long, you guys. So helium can only be made in the sun mostly, or in very small amounts on Earth, like very small. And it's actually a super important thing as far as science goes. And it's very it's very rare. It's not actually that common. And everyone's just like, oh yeah, we'll put it in balloons, call it good, let it go. Because once it's in the atmosphere, it's very hard to get out of the atmosphere. It's not going anywhere, but it's difficult. But there's like underground pockets of helium kind of all over the world. And so that's kind of the fastest way to harvest it. And then we need it for science. And instead of using it for science, we just throw it to balloons. There was a time, I can't remember how long ago, I think it was in the late 90s, that there was a helium shortage because people couldn't find these pockets. And so prices for helium, like a helium balloon was costing people like $200 or something like that. Like it was something ridiculous. So yeah, just keep in mind that sometimes, we have things we use as a everyday product that is much more important for science. Okay, so fusion is safer, uses safer products and creates safer byproducts, but the amount of energy required to go into it is more than it's worth, right? So you have to use a lot of energy just to get fusion going, and the products are not in abundance available. Whereas fission, the products are a lot available, and they give us just as much energy essentially. With one issue being these byproducts are bad, right? So keep that in mind. Yeah, we'll go to the next page here. All right, so one way to kind of read this graph is the split here is at 60 and 120. So lithium, for example, lithium has a nucleon number of 7, right? And it has 5.6, 5.7 mega electron volts by energy, which is enough, but not a lot, right? What's important here is where do things undergo fission and fusion. So, okay, anything 120 or higher. So, any elements that are 120 or higher, okay, those are going to undergo fission. Can any elements that are 60 or less undergo fusion? Okay, 60 or less undergo fusion. All right. And so what that tells us is that kind of we can use fission to move elements in this direction, right? Fission moves elements in this direction, and fusion moves elements in this direction. But these kind of in-between elements, these are the byproducts that we can't really get rid of, right? Because they're not going to give us energy. And so the energy comes from kind of either side of the spectrum, all right? Okay, so this is looking back at binding energy and curve, all kind of stuff. There's a large difference in binding energy between small nuclei, and so there's kind of, this is how we get this reaction happening. Okay, you can read through this. It's basically how we use a magnetic field and stuff to create kind of an idea, a plasma that does go through reaction. Now, if someone can ever figure out how to do fusion reactions, safely and more efficiently, they're going to be multi-billionaire. Okay, so this is basically one fusion reaction, right? So in order to find a fusion reaction, you have to find the change in mass, and then you have to use E equals mc squared to solve it, right? So the change in mass is going to be the mass of the left side minus the mass of the right side. So I did the left side, which is our deuterium and tritium, right? Then I did the mass of the right side, which is our neutron and helium. Added them together, subtracted them, and my change in mass, the difference in mass, so the difference in the binding energy, is 3.14 times 10 to the negative 29 kilograms. Use E equals mc squared. Use E equals mc squared, and I get 2.826 times 10 to the negative 12 joules. Okay, so this kind of gives us the idea that for every time we do this, we get this little amount of energy. Again, not a lot. But remember, this is per atom, right? This is per atom of helium we create, right? So it seems small, but this reaction happens billions and billions and billions of times for a single gram, right? So that's the important part, is for a single gram, this happens billions and billions and billions of times, right? So again, the numbers seem small when you look at it per atom, but if you look at it per kilogram, you're talking about a lot of energy, okay? So yeah, that's it. Sorry, this is a longer video. The next chapter, or the next chunk, is chapter 17. I'm going to do it all in one video. Again, it's going to be longer, but there you guys are done. So yeah, have a good one. Thanks.